Hello, everyone. Today we will be discussing a very interesting subject that covers several projects, several class projects that we have been seeing in the last few weeks. So this subject is called evolutionary computation theory and application. Okay, so I will try to cover first what is called the function optimization. And what do we mean by function optimization? Maybe when we discussed the idea of linear programming, we figure out that we used to have a function. This function has a description based on a real life problem with a set of constraints. And of course, to optimize a function, we actually in searching for a solution for this function via finding the optimal or the best decision variables, as we discussed before. And there are several methods that we used to use in order to solve this type of problems. I will try to cover simple and provide simple idea about the traditional approach for searching this kind of problems. What are the algorithms that already exist and we have been using for a while? And then after that, I will go and cover the big idea of computational intelligence. And then I will talk about evolutionary computation as one of these tracks. And then I will talk about some application. So function optimization is, there are many ways of doing function optimization or solving a search problem. So we have been discussing some of these methods like breadth first, depth first, and there are many other search algorithms that is in the literature. And also there are something called informed search, which is more like have some exhaustive nature like A star and best first algorithm. And all these algorithms provide solution, but it was found that these solutions are not global in nature. And when I use the word global, I mean like there is no guarantee that these solutions are the optimal one, because most of these solutions sometimes are biased by what we call as initial condition or point of where we started the search. So I will try to discuss this and discuss specifically what is known as a gradient descent and Newton method, how they work for function optimization. And gradient descent is one of the common techniques that is used for artificial neural network. I think one of the project is talking about neural network. And then after that, I will show how the effect of providing or using an initial guess or an initial condition can help to speed up the search for getting a solution. And I will discuss the cases where when the search algorithm becomes very complex, we might stuck by or have some problem. So, uh, steepest descent or gradient descent is an algorithm for finding the nearest local minimum solution of a function with the assumption that the gradient of the function can be computed. Now let's try to translate this to English. Now when we say uh, local minimum, so this means that if there is a local minimum, means that there is a global minimum, and if there is a minimum, it means a function is defined in a space where there is an opportunity to search this space. And when I talk about the nearest local minimum, so it means I am starting at a certain point in the space and I'm searching around this point to find the local minimum. That's why we call it local minimum. So there is it's like I do not have the capability to look globally at the search space, especially if the search space is huge. And if the search space, for example, has 100 points to search, maybe I can do exhaustive search or brute first force. And if not, maybe I have to if the search space has 1,000 or 10,000 or a million point. Now in this case, exhaustive search will not do the will not really help. So we will be looking for a local minimum. And the gradient descent means like if this function that we are trying to solve can be differentiated or has a derivative. Okay, because some functions deriving getting the derivative of the function is going to be like very complex. So we need to put an assumption that this function can be differentiated. So that's why this method of Steve's descent are called gradient descent, because the function must have a gradient or can be differentiated. For example, if I have a quadratic function like this, f of x equal 5x minus 3 squared plus 4, and if I would like to find the minimum or the maximum of this function, and we'd like to show a graph of this function. So this function is a function of x. It's only one decision variable, so I can draw the relationship between x and y here is going to be f of x. So if I put x equals 0, so y will be 4, and if, if x equals 0, so this will be 5 times 9 plus 4, and if x equal 3, then this will be 4. Okay, so we can draw this function. And to find the minimum and the maximum of a function, normally, in order to do that, we differentiate the function with respect to the variable x and have the result equal to 0 and then solve for x. So if I plot this function, as you can see, so this function is at when x equals 3, it will give me a value of 4. And when x has any other value, it goes up. So as you can see, when we have x equals 0 on the left here, so y equals 49. It's 5 times 9 plus 4. Okay, so that's the case. 45 plus 4 give me 49. So if I look at this function, if I can present the function as we did in the linear programming case, I can visualize the function so I can pick up the point of minimum. That should be easy. All right, now, since the coefficient of x squared is positive, f has a minimum value at x equal 3, so f of x equal 3, and the value of the function will be 4. So the graph is a parabola that has its vertex at 3 and 4 here on the bottom, and opens upward as sketched here, and this will be definitely the minimum of this function. Here is another function. This is a quadratic function. Again, x 2 times x minus 2. So when x equal to 0 here, so we have the value of the function is 2 times 4 plus 5. And when x equal to if I would like to get this point when x equal to 2, so this will be 0, and the value of the y will be 5. So I can draw this function again. I have the minimum here at 2 and 5. So this is a simple kind of functions that you can draw in x and y dimension, or x and y domain. So in general, we say if we have a function, a quadratic function, of course, this is a specific type of functions, f of x. It's like the function that we did in one of our, actually two of our homeworks, which is a summation of xi squared from I equal 1 to n. That was one of the functions that is a quadratic. So we say if we have a function in the form of a times x minus h squared plus k, so the maximum or minimum of this function will be at x equal h. So here, when x equal h, so this term will be 0, and the value of the function will be k, either minimum or maximum. You got the idea? So here, when x equal h, okay, if h is 2 or 3 or 5 or whatever, when x equal h, this term will be 0, and then the value of f of x will be k, all right? So this will be a minimum or a maximum, all right? So that's a representation of to solve this simple problem. Now, to find the function, if I have a function like this quadratic and I would like to formulate it, we can formulate this function and make it in a form of a quadratic function with this format, f of x, a times x minus h squared plus k. So we can do that here in this example, and then we can know that the optimal of this function is at x equal 5, and the function peak or minimum is at minus 6. All right. Now, there are other methods to solve function optimization. It's called iterative method. And iterative method basically or simply depend on the gradient descent of the function. So if I have a function like x squared here, this is x squared. So this function has a minimum at x equals 0. So this function has a minimum at x equals 0. So if we selected a certain value for x at x equal at time, so if assume this is time t or instant t or iteration t, so if x, let's say x equal 1, so the value of the y is here if I substitute it in the function. Now what we do in order to move from this point down the hill to this point is actually moving step by step. And in order to calculate the steps, so this is x of t minus some constant alpha, and alpha is here and the iterative factor. This could be like a small value or bigger value, but we prefer it's small because this is a step. And then the nabla f of x of t, this is the differentiation of the function. So this is a gradient of the function. So what we try to do is we try to get the you can call it a form of update to the position of x. So if x of t is a certain position, now if I want to get x of t plus 1, so it's like I'm adding a delta x of t. So it's like a kind of movement. And this movement is actually calculated based on what we call as alpha, which is the step size and the gradient of the function at x of t. And when I say the gradient, it means the differentiation of the function around x of t. So for example, if I have f of x equal x squared, so this means that the differentiation of, so it's nabla f of xt is going to be 2x. All right, so that's basically the idea here. Now this is I'm going to show you like a simulation. This simulation is actually in MATLAB, just for simplicity reason. It shows how the this idea is provided here. Let's see it.
I would like to show you the conversion of a function if we do it step by step. If we have the function x squared, for example, so x squared, we know that the minimum of this function is going to be 0. So because when you differentiate f, so it becomes 2x, and then when you equate x to 0, so the minimum of the function is at x equals 0. So I will run this simple example here to show how this works. So assume first I have the function f of x equal x squared, and I have a step size is 0.01. Okay, let's start by just 10 iteration and see what's going to happen to this function. So if I run this function here, I can see I can have like 10 iterations. So the first iteration I started by a value of x equal 1, then we move down to 0.98 because we are minimizing and so on. So we go down, down, down until we reach a value of 0.81. As you can see here, 1.98, blah, 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 till there. Now let's try to increase the number of iteration to, let's say 50 iteration and see how you're going to go down more. So when we run that, as you can see, so we are trying to approach or reach the value, the minimum value of x, actually the optimal value of x and the minimum value of the function y. So the minimum value of the function y is going to be 0. So minimizing x squared, minimizing this function is going to be 0 at x equals 0. Now let's increase the number of iterations instead of 50. Let's make it 300 iteration and see what's going to happen. As you can see, we keep going down, down, down until we reach some value which is 0.0023. So we are approaching almost the value of 0 in this case. Okay, so differentiating this function will lead to x squared go to 2x, and 2x when equated to 0, to get the optimal value of x, we get the optimal value of x is 0. So this is the same way. By the way, the step size might have some different effect on the iteration and the progress. For example, if we have a step size like 0.1, let's see what's going to happen to the function. So we have a larger step size. As you can see, we are getting very fast to the solution, although we have a number of iterations. But if we look carefully, okay, so the value of 0 is like very early. So if we have a step size of 0.1, we maybe can reach the solution like in 20 iterations, for example. Let's try the 20 iteration. As you can see, we are almost there, 0.001. So if we go for 30 iteration, for example, with a bigger step size, So we get to the 0.0012. But by the way, the step size is actually selecting it is very critical. I mean, large step size or a small step size, it depends on the characteristic of the function. Because, for example, if you have a large step size, you might keep jumping between the right side and the left side, so you don't know what is the best. So you need to keep selecting a good step size. So, for example, if we make a step size like 0.5, let's see what's going to happen. Okay, we got it like very, very soon, right? But jumping like this, it means you might miss or lose some variations between 0 and 1, right? So maybe the function itself has some variations in between, so you're gonna miss it. So this is very critical. So this is a demonstration to show how we do functional optimization using gradient descent with the different steps. Of course, you can change this function and do, like change the values if you want. Thank you.
So here is a more detailed example on how the process for calculating the gradient of a function happen. So when I say xi equal xi minus 1 minus epsilon, which is a step size, it should be bigger than 0, and f prime of xi minus 1, which is a differentiation of the function f of x. Now, we are seeing now a function f of x equal x cubed minus 2x squared plus 2, and we define the step size epsilon equal to 0, and we start at initial condition x0 equal 2, and we gonna try to move from one step to another. So the idea here is we can of course change this epsilon depending on the value. So if I start here at this point of x0 equal 2 here, so and then we did calculate the differentiation of the function and then substitute in to get the new value of xi. Of course, this can be xi and minus 1, and this is xi, or this is xi and this is xi plus 1. So it's an iterative process. So we move from step 1 to step 2, step 3, and so on. This is exactly as we saw in the previous video. So it starts at point xi and as many times as needed moves from xi to xi plus 1 by minimizing along the line extending from xi in the direction of f of xi. So this is like a downhill. And by the way, when you look at this function, if you draw it over a large range or large domain, so we are here because we started at this point x0, we reached this minimum. Okay, but of course, if the function has a different characteristic, maybe it has another minimum in this side, so we will not be able to reach it, and that's the reason. So if we draw this function and if we run the code one more time, we see that this is going to be the output. So we start at point 2 and then we keep going down till point 1.3, which is almost the optimal value for this function x cubed minus 2x squared plus 2. Now, there is another method which is called Newton method, and this Newton method simply is working by, again, using the gradient, but the way we update the position is actually by another term or another delta x, which is f of x at point n or point 0, 1, or 2, 3, it depends on the iteration number, divided by f prime of xn. So we substitute by the value of the function divided by the differentiation of the function at the same point that we have. Okay, so we say we keep doing this until if xn minus xn plus 1 is less than the desired accuracy, like if you keep doing this until maybe you say, okay, I'm satisfied if the error or the difference between the steps will give me like is 0.001, for example, then we can say, oh, we reached the conclusion. So it depends on the user requirement or the problem requirement. So sometimes we can accept an error of, let's say, mean square error of zero point 0.5. In some cases, we might need an error which is 0.0005. Okay, so it depends on the problem, how complex it is. So this is an example that shows a function f of x equal x squared minus 2, and we use x equal 1 as an initial guess or initial condition. And of course, if we got f prime of x, the differentiation of this function will give me 2x minus 0. This is going to be 0 because this doesn't have an x term. So f prime of x will equal 2x. and we can now use the formula. So we start substitute to get x1. So it's going to be x0, and x0 here is 1 minus f of 0. So the substitution of the function at x1 is 1. So this is 1 minus 2 will be minus 1. And the differentiation is going to be 2 times 1 will be 2. So this is the term here will equal to 1 plus 1 divided by 2 will equal 1.5. Okay, so this is the operation that we are doing here. We substitute. So we start by point 1.5, and then in the next step, we repeat the process, but now x0 will become, instead of 1, it will become 1.5, and we do this, so we get a point of 1.42, and next one will be 1.41, and so on. As you realize, note that the answer is getting closer to the correct answer, which is the square root of 2. Because this function, actually, if you would like to get the minimum, so you put f of x equals 0, so x squared will equal 2, so x will be the square root of 2, which is equal to 1.41. So this is an iterative way of reaching the optimal solution for a problem, okay, using Newton method. So this is another method to show you the traditional approach of solving. So here we have constraint, which is the function must be differentiable, and we have to select a step size accurately so we do not jump over the search space or the function characteristic and might lose the optimal solution. So in order to do that, we always, like plot a table which has n, the iteration number, xn, f of xn, the differentiation, the division, and the substitution like this. So that will give us the solution. Here, this is a solution for a parabola. So this is a function of sine x, and we are showing how this function works. So this is actually in MATLAB. There is a code a function minimum with boundary, and this is you pass the function fun, and you pass the boundary x1 and x2 and some options if you like. So display the iteration, and that gets you the minimum of a function. So this function in MATLAB actually helps to minimize any function x. As you can see, this is a manual. And of course, you can write the function as a function of x, and you write whatever function you like, and you identify the domain for x0, the initial condition for x0. Now here we have actually two variables, x1 and x2, and you can feed it, and then the function will be, you will get the optimal value for the x's and the optimal value for the function at these x's. Okay, and this is also another simulation for some of these functions, and this is a conversion reaching the optimal solution. So this is the start of, when we talk about a conversion curve, so this is a curve that shows after each iteration how the function value is converging to its optimal value. So we are talking here about iterative process where you reach as a solution from x0 to x1, x2, blah, 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 until you reach the optimal solution of a problem. Of course, there are many test functions we use for numerical optimization. These test functions are commonly used to test the algorithms that we are adopting here. So, where you can test the conversion rate, the precision, the robustness. This is if you click on this link, that this link should provide a link to a website which has test function for optimization. So these are some of the test functions that we studied while doing our homework for genetic algorithm and BSO. These are some of the functions that we use. So this is numerical functions we use to test our algorithm and see if they are working good or not. So that's the layout of the function, like clustering, Rosenberg, and Bill, and Ackley, and sphere function. This sphere function is one of the common functions that we use to see how fast is our algorithm's convergence. So this is again a test function for numerical optimization problems. So now the question that might be arises is, how does the initial guess speed up the conversion? Of course, if we pick up lucky enough to pick up an initial guess that is close to the optimal solution, we will converge very fast. But if it is far away from the optimal solution, then it's going to be very hard to reach the conclusion. Of course, the question is, how do we know that? There is no way to know that. Actually, for example, in some cases, studies like artificial neural networks, which is one of the project is talking about artificial neural network and using feed-forward backpropagation learning algorithm. Backpropagation learning algorithm is again a gradient descent algorithm. It depends on the calculating the gradient of a function. So the weight itself is going to be updated using an iterative method based on the gradient descent. So if we can calculate the gradient for the function, then we can move step by step to reach the solutions. We need to make sure that, as I was mentioning, neural network, for example, or backpropagation learning algorithm has a problem, which is it's an algorithm that can stuck by local minimum. So sometimes when we run the neural network, we might not get a good result because the initial condition of the weight is not in the right place in the search space. So we might need to rerun the algorithm one more time with a different weights. Okay. Now, if we would like to look for what we call as a search space. Now this is again the quadratic function. So it's a function that, if we look carefully, has a minimum here at value of, if it is ax squared, so it's at value of 0, or if x equals 0, it will be a value of c, which is a constant here. So if I look at some of this test suite, this function is called the Young function. The Young function. This is a quadratic function. In this is has two decision variable x1 and x2, and f of x is actually the sum of xi squared from I equal 1 to 2, and this is the surface of this function. As you can see, if you start from any initial condition somewhere on the surface and you move with a certain step size, you after some time you will reach the optimal solution on the bottom here. So this is the main point on the downstreams. But of course, if you have a function which has this blue characteristics, is, as you can see, it's not going to be easy, because every time you start by an initial condition, you might end up to a certain minimum for assume we are looking for a minimum for this function. So if I started at this point, here, for example, then I can move with a step size, blah, blah, blah. I will reach this point. Okay. But if I start here, I might get to this global minimum. So this is a local minimum. This is a local minimum. Okay. If I start here at this point, I will again reach a local minimum. So finding the global minimum is actually a very important issue, because finding a global minimum is a solution for a problem. And we are always looking for the global solution, because that might save us money, that will save us, increase our profit, and minimize our cost, and so on. So in many different problems, this algorithm can help in achieving a good solution for a problem. Now, the search space that we are talking about so far seems very simple and not that complex. But if we would like to look at some other functions like this function, now we find that the search space gets more complicated, and actually the initial guess will not help. If we look at a function with this characteristic, it becomes harder. If we look at some function like this, strings, is going to be much harder. So these kind of functions are really not easy function to find the minimum or maximum if we start at certain initial conditions. So things become more complicated, and our current algorithm for searching for a solution most likely will fail to get the optimal or the best solution for this function. Also, another challenge, which is when the function that we are trying to solve might have multiple peaks. So for example, multiple peaks or multiple minimum in this case. So this function, for example, if you look for maximum, you have several peaks, and all these peaks has the same optimal maximum. Okay, so which one we should pick? Actually, this is a nice type of problems, because you can have alternative solutions. So we put in front of the designer various solutions they can pick or select, based on the resources or based on the available decision variables importance in every certain case. So that lead to part two of our presentation here, which is computational intelligence. So computational intelligence actually is a successor of artificial intelligence, and it relies on what is called heuristic search. So it actually has several pillars or several branches. They are three. There are three. The one is called fuzzy systems, one is called neural network, and one is called evolutionary computation. And one of the famous evolutionary computation algorithms is genetic algorithm and particle swarm optimization, and many of the algorithms that we discussed in some of the project in class. And that's why I intentionally selected these topics to talk about here in class, so you better understand the deepness and the importance of these algorithms for future use. Okay, so computational intelligence actually combines learning, adaptation, and evolution to intelligence and innovative application. So, and evolutionary computation actually it's inspired from Darwin notion of natural genetics, and we will see some nice little movies about this. So computational intelligence, as we say, it includes neural network, fuzzy logic, swarm intelligence, and evolutionary computation. And evolutionary computation actually has several fields like genetic algorithms, genetic programming, evolutionary strategy, evolutionary programming, and these are very, very famous techniques and methods. And these algorithms actually prove to be very successful and efficient in solving optimization problems. This is another layout of computational intelligence. As you can see, neural networks, backpropagation neural network, self-organizing map, hopeful network, feed-forward neural network, which is the one that we are discussing in one of the projects, genetic algorithm and genetic programming. Genetic programming is one of the very powerful algorithms for solving optimization problems, and particle swarm optimization. This one, we talked about it in details in class here, was one of the projects. So in general, the primary goal here is actually to solve problems, to get the minimum of a function subject to certain constraints, as we did in linear programming, and equality constraints. So we have equality, we have inequality and equality constraints for any of these problems. Of course, if there is no constraint, the solving the problem will be easy. But if there is constraint, there is going to be lots of effort we need to spend in order to handle or solve this type of problems. So in this part of the presentation, I will talk about what is evolutionary computation, what are the main streams of evolutionary computation, the well-known paradigms, and what are the main components of evolutionary computation. And this most likely applies on genetic algorithms and some domain of application, how they work, and then we talk about GA and how can we formulate a problem using GA. So evolutionary from biology, let's see how this idea was inspired from biology.
This episode of Stated Clearly was made possible through generous donations by Bird and Moon Comics, Proof Avenue, and contributions from individual viewers like you. Stated Clearly presents, what exactly is evolution? In biology, the theory of evolution doesn't tell us exactly how life began on Earth, but it helps us understand how life, once it came into existence, diversified into the many incredible forms we see now and in the fossil record. It also helps us make sense of the way in which modern creatures continue to adapt and change today. In biology, evolution can be defined as any change in the heritable traits, those are physical traits like fur color in mice, spots on the wings of butterflies, or instinctive behaviors like the way that dogs greet their friends with a sniff, within a population across generations. This definition can be a bit confusing, so let's see how it works. All healthy living things, from single-celled amoebas to flowers to dolphins, are capable of reproduction. We have children, we make copies of ourselves. We do this by duplicating our DNA and passing that DNA on to future generations. DNA is a chain-like chemical stored inside each one of your cells, which tells them how to grow and function. Your DNA contains coded information on how to build you. The information in your DNA is different than that of, say, a daffodil's DNA, which is why you look and function differently than a daffodil. The information in your DNA is slightly different than that of Elvis Presley, which is one of many reasons you don't look or act quite like he did. Single-celled amoebas and other simple creatures reproduce by copying their DNA inside their guts, moving both copies to either side of their body, splitting in two right down the middle, and then growing back to full size. If all goes well, the two new amoebas will be exact copies of each other, but in nature, things aren't always perfect. When DNA is being copied, errors can occur which modify the DNA code. This is what we call a DNA mutation. These mutations, which happen completely on accident and randomly to any part of a DNA strand, can produce variation in the body shape and function of the creature who inherits the modified DNA. In this case, our new little friend has an arm that stretches extra long. If he survives long enough to grow and reproduce, that extra stretchy arm, which is now coded for in his DNA, will be passed on to his children. Evolution. Any change in the heritable traits within a population across generations has officially occurred. Reproduction for dolphins and badgers and people is a little more complicated. We have to find ourselves a partner. When two badgers get together and, fall in love, a sperm cell from the father, which contains a copy of half of his DNA, only half, combines with the egg cell of the mother, which contains half a copy of her DNA. The result is a brand new cell with a complete set of DNA instructions, all the information needed to divide and grow up into a brand new badger. The new child matures to be similar to her parents, but also unique because she develops some traits from her mother's DNA and some from her father. Her new combination of traits can be passed on to her children, and again, evolution. Any change in the heritable traits within a population across generations has officially occurred. Besides a unique recombination of her parents' traits, she might also have developed some completely new traits of her own due to DNA mutations. Maybe extra hairy ears, for example. If she survives long enough to have kids, her DNA will combine with the DNA of her partner, and she'll pass on those extra hairy ears to at least some of her children. Again, evolution has officially occurred. So there you have it. Evolution is really pretty simple. Scientists and normal folks everywhere witness evolution happening all the time. Small changes like the ones we've seen here can add up over multiple generations to create dramatic changes. If you were to go back in time just a few thousand years, you'd find that all dogs, for example, originally evolved from an ancestral group of gray wolves. The evolution of those wolves from generation to generation was guided by humans. People were selecting wolves with the traits they liked, letting them breed, and then only keeping the puppies with the most desirable traits. As time went on, different breeders preferred dogs with different features. Some selected for large size, some for small size, some for brains, others for brawn. Today, wolves have branched out into hundreds of breeds, very few of which look and behave much like their ancestors. A massive amount of observable evidence from many different fields such as genetics, chemistry, paleontology, and mathematics overwhelmingly suggests that just like all dogs share a common ancestor, all living things, me, you, pufferfish, banana trees, if you go back far enough, also share a common ancestor. We are literally related. We don't know what the first life form was or exactly how it came to be, but the simple process of reproduction with variation over billions of years looks to be responsible for all the diversity of life we see today. Now, you might be saying, wait a minute, hold on here. Isn't evolution random? To do something functional like turn a wolf into an adorable mini poodle, random evolution had to be carefully guided by an intelligent dog breeder. Researchers claim that all mammals evolved from an ancient shrew-like creature. But the difference between a shrew and an elephant is far greater than that of a wolf and a poodle. Who guided that process? Who was the breeder? In the mid-1800s, two men, Charles Darwin and Alfred Russel Wallace, independently discovered that a breeder is not necessarily needed. There is another force capable of guiding random evolution to produce order and complex function. They called it natural selection, which happens to be the entire topic of our next video. But before you move on, let's recap what we've learned so far. Biological evolution is any change in the heritable traits within a population across generations. All healthy living things can make copies of themselves, but they do so imperfectly. Small variations can add up over generations to create dramatic differences in the body form and function of living creatures. Evidence overwhelmingly suggests that all life on Earth is related. So remember, next time you invite family and friends over for a holiday feast, you're actually just inviting family. That includes the turkey and the pumpkin in the pumpkin pie. I'm John Perry, and that's evolution stated clearly.
All right. So, as you can see, this idea of evolution is coming from biology and coming from nature. And the area of evolutionary computation is actually a combination between evolutionary biology and computer science. So there used to be a conference in Germany a long time ago related to natural evolution, where scientists and physicians used to meet and discuss several, ideas that related to the human body and the biology and nature, and how these ideas can inspire computer scientists to develop some algorithms that can be used to solve real life problems. So this is a nice book for computational intelligence if you are interested in looking further in this idea. So again, what is evolutionary computation? Evolutionary is an optimization process that aim to improve an organism or system ability to survive in dynamically changing and competitive environment, which is very important. Dynamically changing competitive environment. And evolutionary computation refers to the computer-based problem-solving system that use computational models of evolutionary process. So these models, as we can see, is actually the idea of it like genetic. When we talk about genetic algorithms, we talk about genes and chromosomes and structures. So it actually evolved from the idea of biology and the natural selection idea of how these solutions can evolve via some parameters called crossover and mutation, and what is known as a survival of the fitness and reproduction is part of this evolutionary computation. So this is evolutionary computation, which is a future of innovation of AI and innovation. And as you can see later on when we talk about the application, to see how this algorithm is really have a diversity of application in nature. So the basic idea here is Darwin notion of natural genetics. So Darwin actually proposed this idea of natural genetics in the 18th century, and it was mentioned that the theory said that in a world with limited resources and stable population, everyone competes with other for survival. This is the idea of survival of the fitness, and the best individuals or the best like character that has the most significant or powerful ability to survive in this changing environment are the one that will survive and live longer than other individuals or other inhibitors. Okay, so this is Darwin notion. The second part of his theory, he said, the second part is as follows. It says during during the reproduction or production of a child from parents. child organism. Random events cause random changes to the child organism. And this is the randomization is actually the essential component for all these algorithms like GA, Crew Search, Gray Wolf, Optimizer. All these algorithms actually has this natural individuals or natural parameter that allow randomization in the population. So it says if there exist there is new characteristics that benefit this organism, it will survive to the next generation of the population. So we have a population of individuals or solutions or chromosomes, and these individuals evolve uh, in an iterative manner, step by step, to produce solutions that are more successful to solve a problem. All right?